Hello world, this is Craig. I mentioned the other day in my last video that I wanted some feedback, or maybe somebody else had some insight on this MOD8-7 board, which is the digital output board, and why they used open collectors on the drivers. So let's look at this board. What we have here is these three larger chips. These are the 74-100 latches. So these two chips are where the high byte or the page of the port is selected, whether you're looking at a port that starts with address 1 something, 2 something, or 3 something. This is where that's decoded. This is the 3 to 8 decoder that selects the actual port within that. And this is the chip that is the final chip select clock strobe that selects which of these three are being strobed. So the signal comes in from the bus through these two bus drivers, which are the 7407s, and these are open collector, and that's where the question comes from. So first of all, let's look at what open collector is. Okay, so we know that if we have a normal TTL, looks something like this. We have a totem pole output, where this is going down to our common, and this up here is our voltage. And if we want this to go to a logic low or 0, we turn on this transistor, and so it sinks any current that's out here and pulls us down to a logic low. If we want this to go to logic high, we turn this one off and we turn on this one. So that one's off. And then what happens is our current comes in from our voltage and goes out this output line. So this is our output line over here. I should have said it earlier. And that takes it up to a logic 1. Okay, so open collector simply is if we eliminate this top transistor. So now all we have is something that comes like this. Okay, so this is our output, and this is our low signal. Okay, so what we do now is this device can only pull this output low down to ground. Okay, if this turns on, this pulls this low. If this turns off, then this basically just floats to whatever something else is pulling it. So kind of in a sense, the mantra of open collector is, either pull it low or let it go. You can't actually drive it high. All you can do is pull it low. It's called open collector because, of course, this is the collector out here. So this is our emitter, our base, and our collector. Or if this is a MOSFET, then we have our open drain. So this is the drain out here. So either open collector or open drain. Essentially, we're talking about the same thing. Point is, with either one of those, it can only pull it low. Okay, so that's the 60-second description of what open collector is. Now, there's several cases where we use open collector, and let's look at when we use open collector, and then try to come back and figure out why they used open collector on this board. Now, open collector is not your best choice because it can be a little bit noisier, and it certainly can be a little bit slower, and it also can take more power. So, open collector isn't the first thing you think of when you're going to put in a bus driver. And when they, on all the other boards of this system, they didn't use open collector. They would just use a normal bus driver for that. So, again, the question is, why did they use open collector on those? So let's look at when we would normally think about using open collector. Well, when we use open collector, so I'm going to just draw our open collector chip as a little buffer here, write open collector with it. So remember, this is our output. Open collector can only pull this low, so normally what we will do is put in a pull-up resistor to pull it high. So the open collector pulls it low. When we don't want it to go low, the open collector lets it go, and then this pull-up resistor pulls this output high. Okay? So one way that we can use this is the open collector chips often have a high output voltage. So let's say that we've got a signal over here, this TTL. So this is going on a 5-volt rail. We can come through an open collector chip, and now let's take this up to, say, 12 volts. And we can do this if we have something out here that runs on 12 volts, maybe CMOS or something. Okay, so use number one is a level shifter. Where we have something that is like from 0 to 5 volts on input, and we want this to swing from 0 to 12 volts on the output. And open collectors, for example, the 7407 they used on this has a 30 volt output. So we can take this 12 volts, 24 volts, we can take this all the way up to 30 volts and be safe on this output. Okay, so that's use number one, is when we want to use open collector as a level shifter. We want to go from something that is a lower voltage to something that has a higher voltage swing. With the open collector output, we can, so in use number two, oftentimes and usually the open collector has the ability to sink much more current than a standard totem pole output. So it has large sink. And in the case of the 7407, that's about 40 milliamps. So that's a lot of current. So we can use this then if we have, let's say that we have some LEDs that we want to drive. So we have our voltage up here. We want to drive a bunch of LEDs even. We can do that because this guy can sink 40 milliamps. So when he goes high, all of these would turn off. When he goes low, this will pull this down to 0 volts, sink that full 40 milliamps, and it can turn on a lot of things. You can turn on a small motor with that 40 milliamps. So use number two is when we have a high current or a high load. Okay. Use number one was level shifter. Use number two, high load. And use number three is when we have a large fan out, which is actually, it's like number two, part A or part B. Because we can have an open collector out or an open collector driver that can then drive many TTLs. Normally we would have a fan out of 10, meaning that one chip can drive 10 other TTL chips. But if we have a very large fan out, like on a bus or something, and we want to drive a lot of chips, then we would use an open collector here. Oops, I forgot to put in my resistor. I think I probably, so I forgot to put my resistor here to pull this up. So this resistor now is what's supplying current to bring all of these chips up rather than the driving chip. So open collector, when we want to do a large fan out, we will use that so that the chip itself doesn't have to drive it. The resistor drives everybody high. Then when we want this to go low, this open collector only has to sink out of that resistor and then a little bit from all of these devices. Okay, so that's reason number three we would use open collector. Okay, use number four is what's called a wired AND, or maybe a wired OR if you're using reverse logic. So with a wired AND, remember we have our open collector device. This is our output. This is our resistor pulling it up. Okay, so he can only pull this low, and so if we have multiple chips that we connect them together and they're all open collector, this isn't going to hurt anything because, the rule is that if you have TTL chips, you only have one output at a time wired together because, if one were high and one were low, they would be in contention and you could wind up damaging something. But if they're open collector, remember these can only pull things low, so we can have as many as we want together. And it's a wired AND, meaning that this one has to be high and that one has to be high and that one has to be high for the output to go high. Okay, and this is commonly used if you do anything that you have done with like the Dallas 1 wire, or if you've done I2C or multibus or SCSI 1. These all had an open collector type of bus structure where anybody along that bus can pull the bus low, and if nobody pulls it low, then the bus is allowed to float high with the resistor. Okay, so a wired logic, like a wired AND or a wired OR, That's use number 4 for open collector. Okay, use number 5 for open collector is a little more complicated. So number 5 is if you have a transmission line. Okay, so what do I mean? If I've got a driver here, and this comes out and this goes through a long line to a receiver over here. Okay, now if I do let's say I do a 0 to 1 transition. So all of this line initially is at ground. I'm going to do a 0 to 1 transition, and so this chip is now going to start to drive this one high to, let's say, 5 volts. What happens is that signal propagates all the way through here, and if we were to look at the signal right here, for example, we would see that as a function of time, the voltage, this signal, there'd be some delay before it even got the signal, and then when it started to come up, it would be, very noisy, and we would have, a period between here and here where this is, logic low and this is logic high, where the value on the input of this gate is indeterminate. And in fact, what we would probably wind up seeing is that at first, we might see a little glitch of high and then some time and then a couple of glitches, maybe a longer period of glitch, but basically we would see a lot of switching in this gate as this signal propagated through here, and the noise and the reflections and all the problems going on with this transmission line, this could be something, even a Schottky gate couldn't do a nice clean transition on this, because this output can be really, really noisy if we have a really long transmission line. So what can we do with open collector? Well, with open collector, you would normally think that you would put the resistor right here to pull this up. But in fact, if you have a transmission line problem, you don't put the resistor there, you put the resistor down here by the receiving chip. Okay, so what does that do for us? Now, if we're doing our 0 to 1 transition, this chip is actually the first to know it, because in normal operation, when we're doing a 0 to 1 transition, when we're at 0, this guy is at 0 and we have current that's coming back up through this transmission line. If we now go through the transition and this goes to 1, that current stops or gradually reduces, but all of the noise from that transition is at this end of the transmission line. So if we measured this end of the transmission line, in the second case where we have the open collector pull-up resistor by the receiving gate, if we measure up there, now that end would be the end that is noisy. And this end right here, if we look at the voltage as a function of time, it's nice and smooth, because this is where the current is being injected. So this chip is actually really the first to know when this transition happens, because this, if we had another chip up here, he could still be switching back and forth, not realizing that the circuit had switched, where this guy up here got a nice clean transition. Okay, so that's a complicated thing, but that's the 5th use that we would use an open collector for, when we have a transmission line problem, and in that case, we would have the pull-up resistor at the very end of that line, or at the very end of the receiving chip. Okay, so now let's go back to our MOD8-7 board. Okay, if we look at the schematic, we're obviously not level shifting here. These are all TTL, the 7400 is all TTL. So, reason number 1 that we would use this if we were doing level shifting, that doesn't make sense. Okay, reason number 2 and 3, I guess, if we're doing a large fan out or a higher than normal load, if we look at the schematic or the functional diagram of the 74100, we can see that it effectively has a 2 TTL load. So rather than have a 40 microamp logic high load, it has an 80 microamp logic high load. So each of these 74100s did count as 2 TTL loads, but even so, there's only 3 of those. So 3 times 2 is still only 6 TTL equivalent loads, and any TTL chip in the 70s worth its salt had a fanout of 10. So we were well within what a normal fanout would be with these 3 chips. So they could have actually had 4 of these 74-100 latches because the decoders are already here. They're not using on these bus decoders. These are all quad chips, and they're only using 3 of them. And so the strobe chip is a quad, so they're only using 3 of those. They could have, for no additional real estate, they could have had a 4th socket here and latched out another port. They probably, I guess, would have ran out of pins maybe down here, but they could have brought it off board up here. Another interesting thing was why they didn't bring out that 4th one, and it's probably related. It's possibly related to why they didn't bring that out as to why they also used this buffer. Okay, so they weren't level shifting. They had a normal load. The load was well below a fan out of TTL. They weren't doing a wired AND, obviously, and they're not doing a transmission line. There's nothing on here that's long enough to merit transition line handling. So, okay, the final question is, why did they do open collector on that? And the first thing I thought was, well, you know, they occasionally lifted things from some of the original Intel boards, you know, like the SIM4, the SIM8, or even the Intellect 8. But I went back and I looked at the schematics for those, and the SIM8, for example, used the 3404, which is just a regular totem pole output on its latches, and the Intellect 8 used a 8093, which is a tri-state on its latches. So neither of those used open collector driver on that. So I went back and I started looking at more about the 7400. Now the 7400 is an interesting chip in that it wasn't very popular. It didn't have a very long lifetime. As far as I could see, only Texas Instruments manufactured it. It was only made in the straight 74 series. It was never made in the low power Schottky or any other series. It was just made in the 74-100, and then it was eventually dropped. So when these boards were laid out, it was a fairly new chip, I think. It was possibly unproven. It was single sourced. It did have higher than normal current input requirements, and I'm guessing that it was somewhat unfamiliar. And you know, maybe simply because it was unfamiliar, they decided to overdrive these 3 latches with these open collector drivers. Another possibility is maybe they had intended this board to have more than 5 of these 74-100s, and they just ran out of pins somewhere else. So for example, down here on the backplane connector, or they decided not to put it something on the top. So because if they had 5 of these 74-100s, then they would be right up to the TTL fan out of 10, and that would have been the limit of a just a standard buffer here. So maybe when they originally set this out, they said, well, let's have 5 or 6 of these 74-100s, and then they needed to have the open collector. But that's just a guess too. My final guess is that possibly they put in these open collector buffers as a means of protecting the bus from these outputs. And that's kind of a hard argument to make because they didn't do any kind of protection on the inputs, but on these outputs, the 74-100, or I'm sorry, the open collector buffers, because they have such a high voltage output capabilities, so they can go up to 30 volts. So if you were connecting to something on the output that accidentally you connected it to 24 volts, that 24 volts would go right backwards through these 7400s. And if these were a normal TTL chip, it would blow right through those and onto the bus. And of course that would do a lot of bus damage. These being open collectors with a 30 volt capability, if you put 24 volts on these latches on the output, accidentally, then it would blow these latches out, these 7400s, but when it got back to this buffer, the buffer could handle that 24 volts and it wouldn't get back onto the bus. So, I'm guessing that that's possibly a likely thing, but what I would be interested in, if anyone else has any insight in this, if they have seen in any of the documentation a description, in the circuit description or whatever, of these mod systems, just as to why they decided to use open collector on that those bus drivers. Okay, so this, it's a small point. It's just something that when I was looking at this schematic and I was writing the code to do some bit banging on this and testing this board out, I just got to wondering why they decided to use open collector on that, because that's not usually the first thing that you look for when you're designing a circuit. So they must have had a reason, and just curious to see if anybody knows what that reason might be. Okay, well, if you can think of anything else, leave me a note below. But other than that, thanks for watching. Talk to you later. Bye-bye.